So, hello everyone. Thank you so much for joining us for today's AIAA Los Angeles Las Vegas section e-town hall meeting. Today I have a very important person, leader in the space program to give us a lecture and a very important speech for the future of the space program. So stay tuned, enjoy the event. Before that, we have few logistics to go over. Let's see. Okay, so first, thank a lot to AIAA headquarters. This Zoom platform is so amazing, and they have been supporting us, and truly highly appreciated. And this event, this meeting is being recorded, and it will be posted on YouTube, podcast, and AIAA Los Angeles Las Vegas section website. Thanks a lot to the speaker, Dr. Jim Green. And just a few words. If your internet bandwidth is limited, please, you can turn off the video and just use the internet for the audio, or you can dial in to use the phone line. That's more stable. And if you have any question, please raise your hand in the Q&A session after the main presentation, or you can type your question in the Q&A. And all our events are networking events, so you are welcome to type in your chat communication in the chat room. But try not to put the question in the chat box because it's hard to differentiate. Okay, so just a few words about AIAA. It's a very distinguished organization, membership-based, nationwide, also have international presence. Our current president is Mr. Basil Hassan, executive director, Mr. Dan Bacher, and our section chair is Dr. Jeffrey Michelle from Raytheon. And we have present in over 88 countries, and they include 95 companies like SpaceX, Blue Origin, Boeing, etc. Headquartered Reston, Virginia. And if you join a professional society like AIAA, you can connect to people that you never really have a chance to meet, and you can see the update for the latest technology and the trends, and also apparently publish work or make presentation, and you can put this on your resume. And different level of membership. Young professional is also professional, but in early career is under 35, but after college. We also recently have the student high school membership. And our customer service is really the best line if you have any question, but you're welcome to contact your local chapter or sections. Become a member, you can engage immediately to connect to the members and experts in the world, around the world, and you receive the daily launch email, insider story, a monthly Aerospace American magazine, and you save a lot for going to AIAA conferences. And AIAA publish with AIAA, ARC, and connected industry, and we have AIAA Foundation for education and awards. Career Center, and a very important feature is the advancement of membership. So for example, if you're a member, you can advance your ranks as it goes in different categories. Senior member, associate fellow, honorary fellow. For example, our Dr. Jeffrey Puchel, the section chair, is a fellow of AIAA. Then we have Mr. Steve Izakowicz, the president of Aerospace Corporation. Then we have Dr. Bill Gerstenmaier, is an honorary fellow, along with several, like Dr. Mark Lewis, former president of AIAA. So it can be in many categories, in technical, paper, or education, etc. Then we have a work, Guggenheim, and Reed Awards, etc. And student membership, you can apply for scholarship if you are a member, and you can attend the regional conferences for students and the different project contests. And AIAA Ascend just took place in November It's a very good program, a forum as to continue that what's left over from the former space conference. The next one will be SciTech in January. Is a combination of different conferences. Just a few words, I know people are very anxious for lecture. Just a quick words for Southern California. There are so many aerospace activities. This is really amazing. The James Webb Space Telescope is going to launch on December 22nd. It's the Northrop Grumman. Then we have Aerospace Corporation, SpaceX, Virgin Galactic, JPL, etc. And a new activity like Launcher Space and Ampere for electric hybrid aircraft. And keep doing events to keep people together. So Professor Madhu Sankavanu is going to lead a space philosophy event. Hopefully he is with us now. I'll check again. And hopefully he can say a few words. And then we also have a newsletter. This is the November newsletter for the current news, recent news, and a member and a subscriber can participate and write article and or even share photos. So our distinguished speaker today is Dr. James L. Green. She is the chief scientist of NASA. He has amazing, career and leadership. That's why we need in this critical time. We are really blessed and lucky to have him with us today. He served as a principal advisor to the NASA administrator and other senior officials on agency, science programs, strategic planning, science policy, and the evaluation of related investment. Prior to his appointment as the chief scientist, Dr. Green was the director of the Planetary Science Division at NASA headquarters from August 2006 to April 2018. Under his leadership, he managed the New Horizons spacecraft flyby of Pluto, the Juno spacecraft to Jupiter, and the landing of the Curiosity rover on Mars, just to name a few. Dr. Green was also the lead consultant on the movie of The Martian. Obviously, his career is just amazing. There's way much longer than we can read here, but you will learn more from him from his speech and lecture. So without further ado, let's welcome Dr. Jim Green.
Ken, thank you so very much. Let me begin my talk by sharing my screen. I have some slides I'd like to show you. All right, let's put this in presentation mode. All right. Are you able to see the slide, exploration of the moon and then on to Mars?
Yes.
All right, super. Thank you so very much. Well, it's just a delight to be here to tell you what's happening in our space program. And I'm going to touch not only on our exploration beyond low Earth orbit with our robotic missions, but also what's happening with human exploration to the moon and then onto Mars and what our current thinking is. But before I get into the new things, we really must preface the importance of the Apollo program. This is our first human exploration of the moon. It happened with Apollo 11 as the first mission, 12, 14, 15, 16, and 17. And as you can see, they all landed on the front side of the moon, on the side that constantly points to the Earth. Now, what we learned from this was an enormous amount, not only of the origin and evolution of the moon, but also the bombardment history of the solar system. You know, the moon as a largely airless body today really preserves the record of what's happening in space. And so we want to really be able to take advantage of that and continue to read the record. Well, from the Apollo missions, we brought back about 840 pounds worth of lunar material. Now that included rocks, it included the soils, mostly regolith, which is ground up rock, and we'll talk more about regolith. And we also brought back cores where the astronauts with tubes forced these cores into the surface by more than a meter or so, and then brought them back. And in fact, Most of that material, more than half of that material, has not been thoroughly analyzed yet. And we do that by saving some of the material we bring back, so that as our capability in the laboratory gets better and better, we then can go back and open and look at pristine material. Well, the rock record we brought back was incredibly important, and we've been able to tease out a whole series of new sets of information. And the first major discovery, I think, that came from the rock record was a support of what we call the giant impact hypothesis as the origin for the moon. And here's how it goes. It starts early on with the accumulation of matter where the Earth is. We call this the proto-Earth, but also other larger objects in and around the area that the Earth is orbiting the sun was occurring, and they too were destined to be able to hit the Earth to form the larger body that we call the Earth today. The one we're seeing now is called Theia. Now, this object, this early object hitting the Earth, was about the size of Mars. What happened is Theia was thoroughly destroyed, and a significant part of the Earth was also destroyed. But accretion is a violent process, and after this huge destruction, pieces started coming back together. Those things, those small explosive materials that were blown away from the Earth, kept falling on the Earth. Those things that were further away, approximately 4 Earth radii away, fell together and created the moon. So in the end, and actually after this impact, we believe only within a few months' time, the Earth and the moon were indeed created. Now, this is a great little overview film from the BBC, and it's actually pretty accurate to what we feel happened. So that means 4.5 billion years ago, the proto-Earth being hit by Theia ended up generating 2 objects. One we call the Earth, and the other we call the moon, and the moon is really close to the Earth. This we believe is what happened. We can tell because the Earth and the moon, from this rock record that we brought back from the moon, tells us that it is Earth-like rocks with the same what we call isotopes, chemical composition. There's so many things about it that tell us that indeed this impact occurred. In addition to that, we put retroreflectors on the surface of the moon, and these retroreflectors that Neil Armstrong put out and several of the other Apollo astronauts put out in beyond Apollo 11, we use today. We take lasers here on Earth, we fire them, hit the retroreflectors on the moon, and then the light coming back, we measure that time difference from when we emitted to when we receive after that reflection up and back to the moon. And therefore, we can accurately determine the distance to the moon. And what we're finding out is the moon is moving away from the Earth about 1.5 inches a year. All right. So this process has been going on since the moon was created 4.5 billion years ago. Now, that also means to conserve angular momentum, these bodies were spinning really fast when they were first made. In fact, we believe on the order of the Earth was spinning 5 hours was 1 day on the Earth. And so as the moon moves away from the Earth, that change in angular momentum indeed creates the Earth to forces the Earth to slow down. And so we see at various times in the past, the Earth went from 5 hours, 10 hours to what it is 24 hours today. Now that means the Earth today is 60 Earth radii away from the Earth, where it started out was 4 Earth radii away. Now that means if you were on the Earth at the time, and that would not be a good idea because it was just cooling off. It was in that what we call the Hadean period. It was so hot that the moon would be an enormous object. The apparent size of the moon would be 16 times what it is today. It would dominate the sky. And then over time, as the moon moved away, it eventually became tidally locked. So not only did the Earth slow down and the moon moved away, the tidal forces between the two eventually also slowed down the moon's rotation until its one day on the moon is one lunar month. And that's why we do indeed see one side of the moon all the time. Now, another fantastic event occurred that's recorded on the moon, and it's based on, once again, the Apollo rock record that we brought back by looking at the date, in other words, the time new rock was created. So when there's an impact and rock melts and then solidifies, we can, through dating, and we use a variety of techniques for dating, typically nuclear fission in the materials tells us a lot about when these events occurred. And so this late heavy bombardment occurred about 4 billion years ago. So several 100 million years after the Earth and Moon were created and things seemed to be stable, an enormous bombardment occurred. And that bombardment blew away huge holes in the moon. And those holes were so large that most of the crust was carried away, causing the mantle, the magma material inside the moon, to flow into those regions. Now, the flowing of that magma into those regions brought up heavier material, iron and nickel, and indeed what we see today when we see the dark spots on the moon, contrasting to the regular gray material all over the moon, those indeed are remnant impacts that have been filled by magma that have come up from the interior of the moon and created these darker regions because of the difference of the heavier materials in that magma. Now, in addition to this bombardment and magma coming out, this volcanic activity also emitted what we call volatiles. These are big gases like water and carbon monoxide and carbon dioxide and many other argon and many other gases that then are also emitted. And in fact, our current modeling seems to indicate that this turned out to have a reasonably long-lived atmosphere. It's still quite tenuous, meaning it wasn't really very, very dense, nothing like the Earth, but actually stronger in pressure than Mars is today. So Mars has a 6 millibar pressure atmosphere. The moon during this time, our models and calculations seem to indicate that it might have been 10 or maybe even 12 millibars, twice the pressure that that Mars has today. It didn't last long, about 100 million years, so that's a little while. But eventually, the fact that the moon was so small and the solar wind was so active began the process of stripping that atmosphere. But indeed, the atmosphere has a chance to do the same things that it does on Mars or Earth. It circulates. And some of these volatiles then go to the cold traps. So you then see the water vapor actually condensing out and falling onto the surface in these polar regions on the moon. Now here's an image of the moon looking actually at the South Pole. We're directly looking at the South Pole, and what we've colored in this image are what we call permanently shadowed craters. These are craters that never receive any sunlight. And that's because the rotational axis of the moon is only about 1.5 degrees, unlike ours, which is at 23.5 degrees relative to the sun Earth line. The sun moon line, it's only about 1.5 degrees. So that means it's literally perpendicular. And therefore, on these poles, it's easy to see that if you had an impact creating a deep hole, that volatiles, these are things like water, carbon dioxide, carbon monoxide, those things that indeed come from the outgassing during the late heavy bombardment, will also collapse and go into these permanently shadowed regions. And then once the moon loses its atmosphere, the solar wind stripping it away, these things have snowed out, if you will, laying at the bottom of the craters, and therefore is a record of that past event. So when we take a really good look at it, now in this particular image, what we've done, the South Pole is directly in the middle. It's where the two green lines cross. That is exactly the South Pole. And what we've done is we've used all the times in one lunar month to show where there's shadows and where there's not shadows. And those areas that are shadows are areas that are permanently in shadow. Now, from analysis like this, we also can see from remote sensing, based on a particular type of sensor, it's called a neutron monitor, we also can see concentrations of water and hydroxyl. So that's H2O and OH. They are shown in this image in these blue areas. We've colored that blue, and purple areas, of course, are where the largest concentration is. So indeed, we now believe, unlike the lower latitudes on the moon, where the rock record says there's no water or very little water in those rocks, we now indeed see that in the north and south poles, these permanently shadowed areas must have a significant amount of water. In fact, the current estimate, out of about 300 of these areas that we have defined in both the north and south hemisphere, several 100 million tons of water, we believe, are in these permanently shadowed areas. So, but there's going to be so much more. And this is where the history of the moon will be important. As we mentioned early on, when Theia hit the proto-Earth and formed the Earth and the moon, there was also cometary material and asteroid material that comes and hits the moon and hits the Earth. The Earth's record for this is gone largely because our atmosphere, our plate tectonics, the weathering, the oceans have eradicated those craters, but that record is there and it's on the moon. And in fact, for every crater you see on the moon, because of our size difference, we estimate 20 for every one of the craters on moon, 20 of that size hit the Earth. And so consequently, we see the moon is of course heavily cratered. And of course, that means comets and asteroids hitting the moon that bring volatiles must reside in the permanently shadowed region. Also, that lunar atmosphere must reside in that permanently shadowed region. It's also during a time when the moon had a magnetic field, just like the Earth, and they intertwined, creating a circuit allowing material from the Earth's atmosphere to come to the moon. And then indeed, there currently is a number of impacts that happen that are micrometeors. There's so much material debris in the solar system that constantly hits the Earth, but it also constantly hits the moon. And this micrometeoric material scuffs up water that's still trapped in the crust, and that will migrate also to the poles over time. So we're thinking that there could be a stratigraphy in these permanently shadowed areas. So rather than go in and dig them up just for the water, we really want to do what the Apollo astronauts did, and that was create cores and study these. Now, these layers might get mixed up a little bit because impacts constantly occur. Ground up rock is the result of impacts, whether it's from large craters, from huge asteroids that are created, or smaller impacts from micrometeors, micrometeorites, also scuffing up the surface. And that's why there's a layer of ground up rock everywhere on the moon that we call regolith. And in that regolith, there's also a lot of oxygen and many other things. So those micrometeors have been hitting the moon for the last 4.5 billion years, as we've discussed. And therefore, some of these layers might be mixed. But without going there and taking a look and getting the stratigraphy, we don't know yet. Now, what else is on the moon? Well, we also see a variety from orbit. We see this from orbit. As we fly over, we see a variety of what we call magnetic anomalies. In other words, regions on the moon that maintain a magnetic field. And these are indeed the iron and the nickel, but also the platinum group metals. Now, here on Earth, we do mine platinum group metals. They're mined in a couple regions, most in particular in South Africa. And they are from a core of a protoplanet that has impacted the Earth. And that core has these large mass molecules, these platinum group metals, and we're mining them out. And in fact, in another 50 to 250 years, many of these platinum group metals from platinum, palladium, osmium, iridium, etc., will be mined out over time. But on the moon, associated with an enormous impact on the far side, called the South Pole Aitken Basin, we see these magnetic anomalies indicating platinum group metals there. So we know then the moon has stored for us in these polar cap areas in particular volatiles that we can use. Water is water, whether it's on the moon or on Mars or on Earth, it's H2O. We go into these permanently shadowed regions and pull out the water. We drink it. We can drink it. We can also tease it apart, have hydrogen and oxygen, and that can be used for rocket fuel. You also can breathe the oxygen. So water, the more we don't have to carry that to the moon, the more appealing it is for us to go back to the moon and leverage those resources that are available. Now, our current plans are really quite aggressive. Over this next couple of years, you're going to see an armada of spacecraft going to the moon. And these are landers in addition to orbiters. We have several coming up in different areas of the moon, many of them in the South Pole, because we want to prepare for our astronauts coming next into that region. We have others that'll be at other locations on the moon to do additional types of science. And we're working with the commercial sector to be able to procure rides to take us to the moon. And here are all the commercial lunar payload groups that are taking us to the moon over the next couple of years alone. So it'll be a tremendous boon in increasing our understanding of the moon, building on all that knowledge that we just touched briefly since I started talking this morning. Now, what about human exploration? Well, one of the big important steps to come together is what we call the Artemis Accords. And these are international guidelines for which we want to work with our international space partners in many different areas. Now, this is very different than the Apollo program, because in the Apollo program, when the Apollo program was a complete US program, although indeed we all know the astronauts felt that this was humanity's step onto the moon, and rightfully so. In this way, making it explicit that we want our international partners to join us is really a huge step, and we call that the Artemis Accords. It's all about peaceful uses of space, making sure we're transparent, telling people, the world, what we're doing, what every one of these agencies that sign up are doing, the interoperability of parts so that one group can build a module and connect to another agency's module, emergency assistance and registration of space objects and exchange and free release of scientific data. Also, a new element that goes well beyond the original Outer Space Treaty, which most of this is based on, is protecting heritage sites. What are heritage sites? Well, we believe, like Apollo 11, the first human footprints stepping on the surface of the moon should be preserved. It should be a heritage site. And I can think of how that would be manifested well into the future as humans begin to learn and work on the lunar surface for long periods of time. They could possibly go down and visit from the South Pole a heritage site, an Apollo 11 site. And so that's a really important step. And so how are we planning to get there? Well, we're building a rocket that is multifunctional in the sense that the Space Launch System will take us not only to the moon, but then on to Mars. And so here we have the SLS and the Orion. We're getting ready now for that first Artemis launch, which will be slated for this upcoming February. So it's a matter of a couple months away. But that's not the only mission that will be going to the moon and orbiting the moon. We have a number of missions that are not only there now, like the Lunar Reconnaissance Orbiter, but new missions that we plan to put into orbit. Artemis 1 will make an appearance in February, as I mentioned, followed by Artemis 2. This will be a crewed mission, unlike Artemis 1, where we're going to launch a capsule that will be censored but not tended by humans. And then we'll learn from that experience such that Artemis 2 will do that same mission profile. There'll be a figure 8 around the moon and come home with a crew. And then Artemis 3 will get down to the surface. In the meantime, we're also building a gateway, a much smaller area to come and dock. We want to be able to use as much of the capabilities as we possibly can, like the same ascent vehicle that we'll put down on the surface and bring humans to the surface. So those are indeed all in the plans. And so where are these sites that we want to go to? Well, we see in this image where the targeted sites are. We have to play off the location, how much light it receives, and how close it is to permanently shadowed regions that provide us resources and access to other material. And so these are some of the candidate sites that we're talking about now for the Artemis 3 crew to land. Now, as I mentioned, in addition to the resources that are in the permanently shadowed region, we also can get access to material that's trapped in the regolith. Oxygen and hydrogen is trapped in the regolith. And therefore, also we find nitrogen and carbon, fluorine, sulfur, also helium, even helium-3, which it would be a nice addition to our ability to mine it and use that as a potential nuclear power source. So these are important things to mine and look at and understand their distribution on the moon. Sorry, my clicker seems to be clicking like crazy, but some of that stuff, like the carbon, nitrogen, and water, are going to be leveraged because we do plan to create a sustainable program. We plan to go to the moon, live and work. We're going to find out how to live and work on a planetary surface by going to the moon first, and do it in a sustainable way. Unlike the Apollo program, where we came back in a matter of a day or two, we're planning to stay many days, several weeks, perhaps several months. And so we're planning to establish an Artemis base camp that will also have the facilities of rovers and the capabilities to support humans, and including the ability to even grow food and provide aspects of sustainability. So I can see that the future of the moon is really all about science and exploration, living off the land. We can once again use the water, extracting that from permanently sheltered regions, and have hydrogen and oxygen as a fuel depot. The material on the moon can be a reservoir for us in the area of mining and manufacturing. So our approach to the moon is really coming along very nicely. And this is indeed the decade of enhancing our enormous amount of information from the current lunar science to really understand what it's like for humans to live and work on a planetary surface. So where are we with Mars? Well, right now, today, there is an armada of missions, both orbiters from many different countries. You see them not only from NASA, but from the European Space Agency, also the UAE and China. And indeed, we have landed assets. We have Curiosity still working, InSight, Perseverance, and also our helicopter Ingenuity, along with the Russian lander and rover. And then on the surface of the moon, these assets have been spread out over many different areas, and we've learned an enormous amount from these. Just like pre-Apollo astronauts landing on the moon, we had many missions trying to understand what the moon was like before we landed. And indeed, these landers providing us ground truth, added with our space assets, really allow us to get a deeper understanding of what's happening at Mars. Now, here's a Mercator projection of the surface of Mars, colored in a way where the reds and the whites are highlands, and the blues and the deep blues are the very lowest spots on the planet. And then you see Zhurong, InSight, Curiosity, and Perseverance are those rovers and landers that are currently on the moon working. The others have come and gone, and we've gained an enormous amount of information from these. Now, in the past, as I'll explain a little better later, the Mars we know today wasn't like that forever. It was a blue planet. It had an enormous amount of water. So that means that water would be in the lowlands. And so where we land in the green and yellow areas, we're actually landing in the ancient shorelines of Mars. And that's important because we're also not only seeing where there's a major geological change with land, water, ocean, and atmosphere interactions, but these are areas where potentially life could have started on the red planet. And that's one of our big questions right now. Did life start on the red planet when it was a blue planet like Earth 4 billion years ago? Or did it never have a chance of starting? So we want to tease that out. Or is it there today, but underneath the surface? Well, when we talk about some of the basic scientific information that we have found out from our rovers and landers, I want to start with Curiosity. Here's Curiosity. It has a drill. The drill actually pulverizes the soils. It's a diameter of about the size of a dime, and it goes down about 1.5 inches. And here are the first two holes that we really dug up on Mars in a place called Gale Crater. And you can see the central peak at the very top of this image. You can see what looks like, on this crater floor, mud flaps from an ancient lake or river that is gone, leaving this sediment in these patty-like features. This is a fabulous area. And indeed, we believe that's what was going on. Now, Curiosity has landed in 2012 on the red planet, and it's made many drill holes, and we brought that material in and we've tasted it. And we have been really surprised by what we've been finding out in many ways. This gray Mars also was the early Mars. Mars soils were very much like the Earth's and early Earth's. And now, when we really look at the mineralogy, we see this huge interaction with liquid water. And we also see key chemical ingredients that we know for life that's important. And those are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Everything, if you pinch yourself, all those things are the basic elements of life, your life. And the soils are moist and there are nitrates. So that's a wonderful, important start because it tells us several things. One, this is an ancient habitable environment. It has the same chemical ingredients that Earth had when life started here on Earth. And today, the soils that are moist and have nitrates are important because we may be able to leverage and use those for sustainability, like growing crops on the red planet. So a fabulous set of observations are coming out from Curiosity that really tells us that this has been a spectacular planet to study, in particular its early history, which may have had life started at the same time life started on Earth. Now, we're also quite interested in, is Mars still an active planet? Here on Earth, we still have plate tectonics, and there's a lot of volcanoes and magma going on. But is Mars active? It's much smaller than the Earth. Okay, so the gravity is 36% that of the Earth. So that means maybe the interior is cooled quicker than the Earth's, and we believe that indeed that has happened. And this instrument, the seismic instruments on the mission InSight, which is a fabulous platform that has weather stations and seismic measurements on it, have been measuring Mars quakes for the last couple of years. It landed in November 2018. And indeed, it has measured well over 700 seismic events that enables us to tease out the size of the core, the mantle, and the crust. Okay. It tells us the core has a liquid outer layer. Now, the Mars doesn't create a magnetic field, and it was hard for us to believe that Mars had this liquid outer layer. That's where the magnetic field actually would have its origin. So that was a surprise. The liquid area is there out on the outer core, but no magnetic field is being generated. Now, it also has a fabulous weather station. Now, this weather station, not only on InSight, we have it on Curiosity, and we also have it on Perseverance, along with all the measurements we make from space, allow us to bring that data in to our three-dimensional global circulation models and model a Mars year. What happens during a Mars year? In other words, these global circulation models can tell us temperature and pressure, wind speed, anywhere on the surface. We've run them forwards and backwards. We've assimilated data. And we now, I believe, have a really good handle on the global weather on the red planet. You can see when these red areas, or sorry, yellow areas blossom like we just saw in this image, that's when the global dust storms can potentially occur. And that's when the sun is beating down on the southern hemisphere. Because of Mars's elliptical orbit, that's when Mars actually is the closest to the sun in its orbit. And that causes this heating and lofts the dust. So this is really important because indeed, for human exploration, we're going to need to know what the weather is like, but also to try to understand the dynamics of the weather on Mars and the physical processes that occur. These global circulation models are critical. So once again, putting all this together, and I've already hinted a couple of these things, we believe Mars started out as a blue planet. It had a significant amount of water for maybe 500 or so million years, maybe as much as 1 billion years or more. And that ocean eventually went through a process of evaporation. So the water cycle got broken where you have evaporation, transport, and rain. In the evaporation process, the water is broken up, gets into the upper atmosphere, and then the solar wind strips it away. And this is where we think Mars lost its ocean over time. By losing its magnetic field and protection against intense solar wind events, which gradually strip the oxygen away, never allowing the water to come back. But let me tell you, Mars has still an enormous amount of water on the planet, not only in the crust, but in the polar cap. Even though we see the polar cap and we see it has a veneer of CO2, underneath that veneer of CO2 is enormous amount of frozen H2O. In fact, that northern polar cap, which is shown in this slide as during the Amazonian era, if we were to melt all that water, 1/7 of the ancient ocean would return. Now, what does this tell us? Well, these discoveries are leading us to a couple really fantastic conclusions. One, that ancient life had the possibility of occurring on Mars because of the habitability of the planet during that time. Lots of signs of ancient water, in other words, both surface, underground. The past geological environments have also a reasonable potential to preserve those elements. That's where curiosity is finding these complex organic molecules. So the soils in certain regions and rocks are preserving that ancient record. So the detection of these complex organics by curiosity are indeed those fingerprints of life. Now, we need to know more about them. We need to go well beyond what curiosity and perseverance is telling us by just sitting there making measurements. We need to bring back a rock record. We need Mars sample return. Now, we know enough about Mars that we can go to the right sites where we think we've got the best chance of getting cores, rocks that we'll bring back that may actually have signs of ancient life in them. And that's what Perseverance is really trying to do. So where are we going to put Perseverance? Well, we're going to put Perseverance on that ancient shoreline, all right? Now, the ancient ocean of Mars, as seen in the upper right at Utopia Planitia, that's where the blue area, that's where the ocean was. Now, about 3.9 billion years ago, an enormous impact occurred. And that's what created this basin, all right? This basin meaning a large crater. Now, in that, there's another area, another crater that occurred about 100 million years later, and it's called Jezero crater, all right? The great thing about Jezero is it's at not only the edge of the basin, it's this basin, this very large basin that also connects to the ocean, but it is right where an ancient river flowed into this area. So you can see in the upper left, this is where the river flowed into the crater, Jezero crater. This is a huge crater. It's 150 meters thick. And so water flowed in here after the impact and filled this crater up. Now that caused the water in the crater to be largely still. But then the flow, when it came in and hit the still water, then the sediments in that water dropped out, creating a delta, much like we see where the Mississippi runs into the Gulf of Mexico. Now, this delta is just a perfect place for us to land. This is where we would anticipate finding ancient life that could have been brought downstream hundreds of miles on Mars and dropped in the sediments and is trapped and now in the rock record. And indeed, this is the area that we landed just outside this delta in Jezero crater. Now, I'm sure many of you have already heard about how we landed. This is, we did this by entry, descent, and landing. We did this with Curiosity. JPL has my eternal gratitude for being able to work this out, making this happen with a marvelous set of engineering capability that they put into it. The entry is where, indeed, we're going to hit the top of the atmosphere, moving 7.5 kilometers per second, and then we have to land on the surface going centimeters per second. And we have to take that momentum out, and we do that in 7 minutes. So we have a heat shield that slows us down. Then when we're at the end of that, we drop the heat shield, pop a chute, that slows us down some more. And then when we are now hovering over the surface, we drop the sky crane. This is a system of retro rockets sitting on top of Perseverance, just like we did with Curiosity, which then hovers tens of meters above the surface, lowering the rover down to the surface. And then once it receives the signals that it's landed safely, off it goes. Now, one of the spectacular images that the Mars Reconnaissance Orbiter was able to take was as it was flying over this area, indeed, Perseverance was on its way to the landing spot. Now you can see pretty close to the center of this image where that landing, where we will land. That circle is where Perseverance landed, and we captured Perseverance undershoot at the time. It hadn't dropped the sky crane yet, but it's on its way down. You know, just an absolutely spectacular image. And then, of course, to the left of this, you can see the ancient delta. Here's another spectacular image from the sky crane looking down as we lowered the rover to the Octavia E. Butler landing site. And of course, Octavia E. Butler is a well-known science fiction writer. This is in theme of naming our landing sites after science fiction writers. And so I'd encourage you, if you haven't read anything by her, please do so. Now, we have landed safely. We're now outside the delta. We're now interrogating the area of the crater floor, and our plan is to move up and start coring rock in the delta using this spectacular rover called Perseverance. It's working perfectly, or as we say in this business, nominally. It has 43 sample tubes, and indeed what we're going to do is we core rock. So at the end of the arm is a rock corer, and this is a tube, a hollow tube that indeed spins, cutting rock, and it creates a tube of material, of rock, about the size of a chalkboard chalk. And so for those of you listening that have never used chalkboard chalk, we'll just say it's about the size of a large Crayola crayon. All right. And then we put it in a tube This is a sample tube. It's sealed, and then we hang on to these, collect several of them, and then we drop them in a particular area strategically that we'll pick up later with another mission and bring them back. And I'll talk a little more about that. Well, this mission is so capable. What is the rock record going to tell us? Well, if we think about the rock record here on Earth, there's more than 5,700 minerals on Earth, but 337 of them are made from interaction with organic remains. In other words, are created from dead life, past life. And indeed, we see a number of minerals on Mars today, and we only know about 250 minerals. So getting back that rock record is going to tell us, really expand our knowledge of the mineralogy and geology of these areas enormously. But we do indeed see many of these minerals that sometimes form biologically on Earth are present on Mars. And that includes quartz and hematite, pyrite, etc., magnetite, many others. Now, once we create these samples, we're going to put them in piles. We'll have, a set of piles, and then what we'll do, we'll launch a mission, M1 in this figure, that will go to the surface with a Mars ascent vehicle, but also a fetch rover. And we'll launch it, we believe, on the order of 2026. We'll then load up from the fetch rover by going to those strategic locations where we put the samples. We'll bring them back to the Mars ascent vehicle. We'll erect that a Mars ascent vehicle, and then we'll blast it off, releasing the capsule, that storage capsule that contains all the tubes that we have created from our rock samples. Then, with an international partner, ESA, their spacecraft will get into orbit. That's M2. Will hunt down that capsule, capture it, also put it in another container, and then bring it back to Earth by dropping it into the desert. And then we'll begin the process of acquiring those samples, curating them, analyzing them, and then, of course, making spectacular scientific announcements. All right, and we expect to do that. We expect to get those samples back late this decade or early next decade. So it's coming up. It will happen soon enough. Now, one of the other spectacular missions that we did attached to Perseverance was our first attempt to fly on in any other atmosphere besides the Earth. And that was with the Ingenuity helicopter. It was actually stowed in the belly pan of Perseverance. That pan was dropped. We drove away. We then deployed the helicopter, dropped that on the surface, drove away for about 50 meters, and then executed some of the testing. We had 5 tests, and this turns out to be a film from the third test, which was an L motion. So indeed, Ingenuity went up on the order of 8 meters, flew, and then came back, and then landed exactly where it took off. Now, this was one of several tests. We had 5 tests planned, and indeed, we see that the total distance that we have gone is 271 meters in one flight. And indeed, the height has gone as high as 10 meters. And indeed, the time has been as long as 140 seconds. So the bottom line is, after the 5 initial flights, we declared the helicopter operational on the surface of Mars. And then the Perseverance team said, look, We won't be able to go everywhere on this crater floor, but there are certain important and intriguing areas we would like to see. Can you interrogate those? And of course, the answer is absolutely. Now, Ingenuity is very limited. It has a downward looking camera and a outward looking camera. It takes those images in, also has an altimeter. And so it only has just the rudimentary set of observations, but indeed, it's done an enormous job in checking out certain areas. Now, this is I'm going to show you a movie of the 10th flight of Ingenuity, where indeed we pick up and we then view these many areas. So here it goes. This is from the downward camera. You're actually looking at the shadow. These were done right at noon. Ooh, there's a reorientation, and now the helicopter is moving off to another another length. Once it gets to another point, makes another turn or reorientation, and then flies another leg of this path that it's going until finally it comes back to an area and then lands safely. Now, this was the 10th flight, and each of these flights have gotten more and more complicated over time. And I have to tell you, this has worked out so well. We just finished its 16th flight. So Ingenuity is working well beyond our expectations. Now, I'll remind you that it was late April, early May on that time frame when we actually first did our first set of test flights. And here we are in December, and we're still flying. And that's just amazing to me. Now, what's happening overall is we're getting ready to study the planet to see if there's past life, but also when we get the rock record, we'll get resources. We'll see what's in the rock record. We'll see if there's materials that can be used. And so there's indeed an important aspect for human exploration. But beyond that, our plan for human exploration of Mars is indeed learning to live and work on a planetary surface, starting with the moon, and then figuring out what we'll need to take going to Mars, what will be there that we can use and leverage, and how we can begin that second process of learning to live on a planet like Mars. Now, one experiment that's also on Perseverance directly related to human exploration was the MOXIE instrument. This is a Mars Oxygen In Situ Resource Utilization instrument. Here it is being installed in the rover. And the concept is it brings in the atmosphere, zaps it, just with a little lightning-like strike, and that takes the CO2, pops off an oxygen. So now you have CO, and now you have O, and as you do more of that, the O's like to combine into O2, such that the end result is molecular oxygen, O2, and carbon monoxide. Now, in the laboratory, this worked great, and we could get a baseline, but how well is it going to work on Mars? The temperature difference between our laboratory and Mars is enormous. What is it going to change in efficiency from doing it in the morning or in the afternoon or in the evening? And what will it be like at different seasons? What is the efficiency of a process like this if we can get it working on Mars? And how would that feed forward to humans? Well, we've now answered that, and the results are fabulous. MOXIE makes 6 to 10 grams of propellant-grade O2 per hour from the air, from the O2 oxygen dominant carbon dioxide dominated atmosphere at Mars. Now, the spectacular thing about that is it worked just so well, it was like it was in the laboratory. And therefore, we can think about extrapolating that. In other words, we need a larger power source and a larger unit, as shown in the bottom right of this. MOXIE today could be sized up, and with enough power, we can begin the process of making 2 to 3 kilograms per hour of O2, and over a 12-month period have enough oxygen to launch a crew of 4 in a Mars ascent vehicle returning to Earth. So, creating oxygen to breathe or fuels necessary, this could play an important role in upcoming human exploration of Mars. So, the elements for the first humans on Mars we're really trying out on the Moon and on Mars. Not only with the MOXIE instrument, but as I mentioned, by the end of this decade, we will be sending a rocket off the surface of Mars. It'll be our first rocket, Mars ascent vehicle. We'll learn how to launch something off the surface of Mars, and of course, humans to return to Earth will have to use that process. We also are investigating a variety of technologies, not only vehicles that we'll use on the Moon, and we'll relate that to Mars, but also different power sources and all kinds of different systems. In particular, getting access to water in the permanently shadowed areas and creating a resource. By doing that, we plan to do that on Mars. Mars has a lot of trapped water. There's a buried glacier on Mars that is enormous, about the size of New Mexico. And in some places, it's 750 meters thick. Our landing spots have got to be somewhere near those areas where we can go in and get access to those resources. So extracting important oxygen and hydrogen out of the atmosphere, with things like MOXIE. Can we grow crops on the surface? What do we know about that? And what kind of nuclear power will we need? These are all the kinds of things that are being investigated. Well, from curiosity, we know that Mars has all the essential plant nutrients in the soils. Can we grow plants on Mars soils? And the answer is yeah. It has all the macronutrients and micronutrients, and therefore we already are performing a variety of experiments to test that out. Now, finally, what is the thinking about humans exploring Mars? Well, right now we're settling in on what we call an exploration zone. One area, about 200 kilometers in size, where we'll land in one area, we'll live in another area, we'll go to different regions to extract resources. This is ISRU, regions of interest. But also we want to go to an area that's scientifically rich, where there's all kinds of new scientific experiments that can be deployed and experiments that humans can do. And also we need the ability to traverse these large regions. 200 kilometers on the surface of a planet is a huge size. So unlike the movie The Martian, we're not going to create different places to go each and every time. We're going to go to one place, and we'll go there for decades, perhaps several hundred years, and develop the site completely, but have the ability over time to extend the range of humans and our ability to explore Mars. And we can do that in new and unique ways because of the fact that we now can aerially fly on the red planet. Now, even though Ingenuity is only about 4 pounds, we believe we can scale that up by a factor of 10. So you can imagine a drone that's 40 pounds in mass, that we then have many more sophisticated instruments, can go much further, can relay its information up to orbiters and back to a central location, and use those in various locations well beyond the exploration zone. So these are some of the things that are being planned. It's just a tremendously exciting era for NASA and for the nation. And many of you in the audience, I'm sure, are going to be part of it. So thank you very much. Let me unshare my screen.
Yeah, thank you, Dr. Green. This This is amazing, very important speech.
Great, glad you enjoyed it.
Thank you, thank you. This is amazing. So everyone, this is amazing opportunity. Please click raise hand or type your question in the Q&A box, but it's better you can speak out. So the first one will be Ben. Let's see. Ben, Mr. Carter, go ahead.
Yes. Can you hear me?
Yes, Ben, go ahead.
Okay. I have a couple of questions. One, about the history of the moon. Was the angular momentum of the Earth-Moon system approximately conserved, or do you have to take the sun into account for that? My second question, before I lose the mic, is what will the future astronauts do about radiation from the sun during solar flares?
Sure. So the first one is yes, the models that create an understanding of the past do have to take into account all the tidal forces. So the sun produces tidal forces, the Earth and Moon have tidal forces between them. And as you dissipate those tidal forces, the Moon therefore moves away. So there's also dissipation that's going on. That's an important part of the process, an important part of the calculation. Now, relative to radiation, we have studied that extensively. We know an enormous amount about it, and indeed, I think initially there was a lot of apprehension about radiation, as it should be, but we're now learning to the extent of how bad is it. For curiosity, we had a radiation monitor on it, a dosimeter. So it sat on the rover and it went to Mars and made measurements all the way there in its capsule. It landed and it's moving around on the surface. It's still working. And so we can gather a total dosage set of information. This has enabled us to take a look at the scenarios of humans going to Mars in a short stay, coming, being there for 30 days or so and coming back, or even a long stay and then returning, and then calculate the radiation that we would expect to have under similar conditions. And what we're finding is that it increases cancer from about 3%, which is what you get on space station, to about 5%. Now, I can guarantee you, if I go into a room with astronauts and I said, we'll take you to Mars, but you have to remember your risk of cancer will increase from 3 to 5%. How many will want to go? Every hand in the room will go up. Now, not only that, a number of new techniques are coming out that we're starting to really realize and understand better, such as repairing DNA, not allowing cells to then replicate in a broken manner and therefore causing cancerous cells. And that's with CRISPR and a variety of new technologies that are coming out. We also have studied certain ways to protect astronauts under certain environments that provide a good storm shelter. And it turns out water is a great way to protect astronauts, encasing them in water. We got to take some water anyway. And so it's a matter of not having a container, but having something that it provides a wall of water that can be used indeed as a small storm shelter. And then, of course, when you're on Mars, half the radiation's gone because the planet blocks it. And even though the atmosphere is pretty thin, it does prevent some radiation. But ultimately, there'll be times when we'll have to have overburden, whether it's in a lava tube or it's a structure that's being made that will also protect the astronauts. It's one of those things that we're going to have to constantly measure, constantly work on, but we don't think anymore it's a showstopper.
Okay, thank you very much.
Sure.
So next, Mr. Mike Helton, go ahead.
Yes, Thank you, Dr. Green. It was an excellent presentation. Very good summary of all the explorations of the moon and Mars to date and what's going to happen. I really appreciate it. My question is very simple, and that is, could there be a consideration of landing at Tranquility Base where Apollo 11 landed for the first return to the moon with Artemis 3? And the idea there is to pick up where we left off at the moon 50 years ago. And the science is, a little bit of science there is to compare what we can find now at that location to what we found 50 years ago. But there are many other considerations that are non-science, not the least of which is picking up the American flag that was blown over when Buzz Aldrin and Armstrong took off, as you know, and that could be something to bring back as a memorabilia from the moon exploration, and planting a flag that won't fall down. And there's many other considerations, including the first female to land on the moon would be really nice to have it land right at Tranquility Base. For public reasons. So that's, there's other reasons too, navigation to land at a spot that we can designate. It's hard to land on the moon where you want to land in latitude and longitude, for example. So that would be a challenge. So I would suggest that that maybe NASA should consider Tranquility Base as a first place to land if they can see that.
Very good input. I enjoyed your thoughts in that area. It turns out NASA would rather preserve the area, keep it pristine as part of a long-term strategy. You know, in another 100 years, no one alive is going to remember seeing or being alive at the time of the lunar landings. And so it will pass from recent memory into even more historic importance. And therefore, the ability to go and visit it in a way that's controlled is much more appealing than trying to land there now today. In addition to that, by landing in a different location, like the South Pole, we begin immediately to then survey the area, since we realize it has a much richer set of resources, not only the mineralogy, the platinum group metals, the water, the carbon monoxide, carbon dioxide, volatiles that we can actually extract and use in the process of future missions by creating capabilities of manufacturing on the moon. So it would be a diversion in our strategy to first go to 11. But as I mentioned, keeping Apollo 11 site pristine is because we do want to visit it in the future, much like archaeological sites that we visit today here on Earth.
Okay, thank you, Jim. I appreciate it. Thank you.
Of course, thank you.
Next, Caroline, go ahead.
Hi, Jim. Thanks for the great presentation.
My pleasure.
My question is, would it be possible to fly an Ingenuity-like helicopter to explore the lava tubes on the south pole of the moon?
Good question. So the moon has almost Zippo atmosphere. And so we've only been able to fly it on Mars. And even then, that was tough to do because Mars's atmosphere is very thin. It's less than 1% of our own atmosphere. I mean, you know, it'd be like flying a helicopter up to 120,000 feet here on Earth. That's what we did. That's what we did. That's the pressure on the surface of Mars. Okay. So it's really a phenomenal step forward. Now, the concept of going in the lava tubes, though, is really important. I really like that idea because we have seen lava tubes on Mars. Okay, they're also on the moon, but also on Mars. What we think is happening in the lava tubes is that they maintain not only a protection of the from radiation, as we just discussed, but also the temperature inside a lava tube, we believe, is nearly constant day and night. Now that's fantastic. When you think about the surface temperature on Mars changes by about 170 degrees Fahrenheit a day. A day, okay? It's an enormous swing in temperature. But in a lava tube, if it stays constant, then it takes us, we then know what kind of energy we need to take it from there into a livable range, and therefore can size our power systems accordingly. Also, we don't know if there's, you know, life in those lava tubes. There could be. They happened early on in Mars's history, during the time it was a blue planet. You know, and so life, when the conditions around get tough, likes to go in the rocks. You know, maybe it's in the lava tubes and more easily found. So I think there's a great opportunity for us to take some of these new helicopter designs, fly into a lava tube on Mars, really check it out, get temperature, pressure measurements, but also really with a set of astrobiology instruments, determine what it might have harbored in the way of life.
Well, I am confident that we're going to be able to do it on the moon and in the next couple of decades. Thanks, Jim.
Well, we won't fly on the moon, but we'll roll around. I mean, we'll still have rovers, and we want to lower them into the lava tubes and take off. Yeah, that we do want to do that.
Next, Dr. Henry Garrett. Go ahead.
Hi, Jim.
Hi.
Can you hear me?
Yes.
Quick questions about some astronaut safety issues, primarily the perchlorates on Mars and the black lung issues with the abrasive nature of the dust particles on the moon and Mars. I know that there's some people looking into that, but that I think those are major concerns that most people aren't aware of, nor do they discuss.
Right. So perchlorates, that is have been found on the surface of Mars. That is harmful for humans, although it can be a source of food for certain microbes. Okay, here on Earth, love different types of perchlorates. So one of the concepts of bringing back these samples is indeed looking for pathogens, not only that, which is probably a low probability, but looking for perchlorates and other environmental chemicals that would be hazardous to humans living and working on the surface. Now, what do we really know about the perchlorates? They're not everywhere. We've only found them in a couple places. Curiosity has seen them, but is now in areas where there's no perchlorates. So it's not like they're ubiquitous, all right? What about perchlorates on the surface? Well, we know if they're there, we can bring the soils into an area where we can flush the perchlorates out and then use the soils, for plant life, for growing in the area. Picking an exploration zone, it will be critical to look and see what that area is like, where there are perchlorates, where we actually can know that they're there, and then use them in the way we want to use them, but also be careful of them as toxins, but then take advantage of the fact that they're not everywhere.
And how about the abrasive nature of the dust particles?
Yeah, so indeed, Mars dust, we don't want it in the lungs. And the reason why is unlike dust on Mars, which is rounded, on the moon, it's very spiky. And that's because when you have an impact, and you tear apart rocky material, there's nothing to erode it. And so once the spikiness of it is created, it remains that way. Now, it turns out dust particles also, regolith on the moon with that structure also seems to accumulate charge. So there's new concepts about using capability to sweep, have an electric field that sweeps out this dust out of the suits. That's one way of being investigated. Another thing that's being investigated is to keep the suits external. So if you can imagine a rover where humans can live and work inside, and then they walk to a surface and jump into a suit, and then the doors close behind them, and then off they go, and then they can work, and then when they come back, they connect their suit and come out of the suit, and then they can live and work without the suit in the environment. Keeping the dust outside is another technique that is a serious consideration. So the dust environment has to be managed. Now, dust, it turns out to be a really important resource. We're going to be taking a bunch of dust, we're going to be melting it, and we're going to be putting it in our 3D printers. And we're going to be creating things that will help us. So the dust, even though it has a problem in getting in the lungs, that we can take care of, we believe, it's an enormously important resource for us. It ground up the rock just in the right way that we can easily melt it. And in fact, in terms of kicking up the dust, on the moon, once we have our Apollo base set up, where we can land and then go to take a vehicle to the habitat area on the moon, that would kick up dust. One idea that has come out is you literally melt the dust and create, like asphalt. You can melt that dust, heat it up and melt it and create your highway. All right. And then stay out of the areas where you'd kick up the dust with your vehicle. As you saw in many of the movies that we did with running around with our rovers on the moon. That's one of the ideas that has been proposed and being looked at.
Is it possible to bring back some of the parts of the rovers to see how the dust has damaged them from one of the later lunar missions?
Well, once again, those are all going to be declared heritage sites, I believe. So we'll probably in the future go visit them, figure out how to go safely. Then we'll have a whole series of things that we'll want to do. But there are a couple rovers on the moon still, that we left. They gave us tremendous flexibility. I think one of the rovers went 17 kilometers. I mean, it's like, all over the place, and then came back. That kind of transportation capability on the moon is really important, and we're going to continue to do that. We're working with several international partners with these ideas. In fact, Hyundai just announced that they want to work with JAXA, the Japanese Space Agency, to build a road vehicle on the moon. And JAXA is already working with Toyota. So we actually have, from our international partners, a lot of interest in driving around on the moon.
Well, then we have that Tesla moving around out there too.
We do, but it's just going to be space debris. It's just going to be space debris. And one of these days, since it actually orbits the sun, crosses our orbit, but also crosses the orbit of Mars, it might actually re-enter on Mars. Who knows?
Well, thank you, Jim.
Sure.
Next, Colonel Schultes.
Yes. First of all, thank you, Dr. Green. A great presentation.
Thank you.
I always learn something whenever, in many things, whenever I hear you speak. So thank you very much.
Great. Good. Thank you.
I'd like you to focus on Mars, and in particular, transit to and from Mars. And you made a statement earlier that radiation is not as bad or insurmountable as we thought.
Right.
Does that stretch to the point of we can do a Mars mission without nuclear propulsion?
Yes, I think so. The concept of nuclear propulsion is to make a rapid transit, and rapid transit just to get out of the solar wind, and that's important. That's important. But I think we'll have to see how that whole propulsion technology matures over the next 2 decades. But in the late 30s, 40s, as the concept is maturing, that's when we'd like to start the process of landing humans on Mars. Now, if we do that, we're going to go the conventional route. That means every 26 months, Mars and Earth end up on the same side of the sun, for which we can leave the Earth going into solar orbit, but in a highly elliptical orbit for which it goes beyond the orbit of Mars before it would return. And of course, we do that just as Mars is there. So we fly out orbiting the sun and go to Mars because we cross its orbit when the planet is there. And then we land. Pardon? So that takes about 180 days. Now, those windows change in time because of the ellipticity of Mars's orbit. But on the the fastest route using Keplerian mechanics is 180 days there. Okay, you can stay on the surface about 30 days, and then you can return. That's going to be about a 220-day return, so it's a little longer on the return in that window. Okay, a long stay is once again 180 days there, but you stay more than a year, and then your return is about between 180 to 200 days. So going to Mars is a long-term proposition, no matter what.
The point is, what is the value of nuclear propulsion in terms of transit times being cut perhaps as much in half?
Well, nuclear propulsion is important because those are some of the same technologies that we want to invest in that will provide nuclear power on the surface. So nuclear power on the surface gives us tens of kilowatts, 50 kilowatts of power or 100 kilowatts of power, enough to heat things, keep things active, charge up all our rovers and capability, and so that's a technology that's extremely important to us.
I agree with that, but that technology doesn't stretch technology as far as nuclear propulsion technologies will require. That is, the temperatures are more like 1500 Kelvin for fission surface systems, but around 3000 degrees Kelvin for propulsion, particularly nuclear thermal propulsion. So being able to crack the nut of nuclear thermal propulsion for reliable transport is much more difficult from a technology demonstration standpoint than fission surface power
Yes.
on the surface of the moon or Mars.
Yes, but it's a stepwise process.
Yes, but nuclear thermal propulsion doesn't really help you from the fission surface power perspective.
Okay. The activities that we're currently doing in those areas is directly with the Department of Energy. Right now, our relationship with them has been strong over many decades. They provide us a variety of radioisotope power. The power systems on the surface today of Mars are RTGs, radioisotope thermal generators. They're on Perseverance and also on Curiosity. They only generate about 125 watts of power. And the half-life of plutonium-238, the isotope that we use, is about 88 years. So this actually allows those vehicles with that constant power to work all the time. It's like, plugging your phone into a socket. So you charge up a battery, and then the battery is used to run your experiments. That enables you to work day and night, and over many, many years, over many, many decades. So we are actually making plutonium-238 and with Department of Energy. So they have a stockpile of isotopes, and we have needs at different power levels. And so those designs are all being thought of and worked with the Department of Energy. But we have some workable designs that we're implementing now.
I guess I'd like to follow up, if that's okay. And basically, the question in my mind, at least, is if it's not necessary to develop nuclear thermal propulsion, why are we doing it? I was always under the impression that cutting the transit time was substantially worthwhile and significant in terms of cutting the radiation dose to astronauts going to Mars, which also has other effects, not just radiation, but even microgravity and the effects on the body as a result of that. And so, but I'm just wondering, I can see nuclear electric propulsion, okay, as being a lower technology drive requirement that could be developed over time and utilized as necessary. And it actually contributes from the reactor side and the energy conversion standpoint to supporting fission surface power systems from a technology standpoint. But nuclear thermal propulsion is a departure. It is directly heating the propellant so that you maximize specific impulse. And maybe it is that you are minimizing the amount of propellant necessary to go to and from Mars. That is really the key to why nuclear thermal propulsion is needed, and not radiation and microgravity.
All these are really good points in the sense that we are investigating many different options. We also have to think about, now I was head of planetary for 12 years, and prior to that I did a lot of work in heliospheric physics. I even worked on the Voyagers, and of course it took decades for the Voyagers to get out to the heliopause, okay, just to cross the heliopause, 120 astronomical units away. Heliophysics groups are thinking about going 1,000 AU with interstellar probe. Our ability to then go from place to place rapidly is not necessarily locked to human missions, but would be a huge boon for us from the aspect of going well beyond the solar system and out to other stars. So the investigation, even though it's what we'd call at a low technology readiness level, doesn't mean it's not important. It means it's going to take a long time to mature, and as it's maturing, we'll understand better its application. Okay.
Dr. Green, we still have a couple of questions. Do you have more time?
Yeah.
Thank you. Manny, go ahead.
Thank you, Dr. Green, for a fascinating presentation. We are creating replicas of the Apollo landing sites in photorealistic detail as fully immersive virtual reality experiences.
Cool.
We have a demo of the Apollo 11 site already. My question is about the moon, specifically about the lunar cold traps. I understand how the cold traps work, but your slides seem to show that there's water distributed over the surface of the moon in areas that are also lit by the sun.
Yeah.
and I don't understand how the volatiles don't boil off when it receives radiation from the sun and light from the sun.
So the instrument that made these observations are sensitive to neutrons. So as cosmic rays come in and interact below the surface, releasing neutrons, the OH, okay, hydroxyl, in addition to H2O, limits the escape of the neutrons. So as you fly over these areas and you see a reduction in neutrons, it could be hydroxyl. Now, how can that happen? What, you know, how is the O and the H getting together? Well, maybe it's being partially implanted, the hydrogen capturing, you know, connecting with an oxygen because of the solar wind. You know, so we're not going to know all of that until we actually get down to the surface and ground truth it, core down, get, you know, even in these areas that receive 20% sunlight. Well, maybe at a glancing blow, because, you know, it's the South Pole, you're always going to see the sun, you know, right at the horizon, or a little above, or when it goes below. Okay. And so conceptually then, there must be something about the quantity of that material that's still trapped in the lunar regolith, more so than water trapped in regolith we know today. You know, regolith does seem to retain a little water. So getting down on the surface and really understanding that is going to really elucidate, you know, the not only the quantity, but whether it's hydroxyl or a combination of hydroxyl and H2O, OH or H2O. Okay.
Thank you.
Sure.
Francis, go ahead.
Yes, I'll just read my question here. How does the role of VR simulations play into habitation planning? What if companies like Google could provide a VR platform that could invite international research that want to contribute and share?
Okay. It turns out we're doing a little VR right now operating Curiosity. So we acquire enough data in and around Curiosity that we can create a three-dimensional framework to walk around in. And many investigators have done that. They've donned the goggles, walked around and looked around and said, oh man, from this perspective, this is a unique view. We ought to be able to go over and get a sample here. We ought to be able to, you know, pulverize the soils right here. So some aspects of VR are already creeping into our robotic missions. Now, how that will extend into human exploration is remains to be seen. But I really like the idea of working in that area to see how we might be able to more easily operate our robotic systems.
Would you?
And we're happy to partner with Google. You know, that'd be great if Google comes in and wants to work with us. I'm sure.
Well, that's great to hear. Thank you.
Sure.
Paula, go ahead.
Oh, hello. This is for me.
No, Paula, Miss Korn.
I'm sorry.
Oh, yes.
Go ahead.
Well, I didn't really have a specific question. I'm taking this all in. And I didn't have at this moment a specific question, but I will say that I'm working on a panel connected with the United Nations, working on rules and regulations on the moon on an international basis. Everyone, Chinese, Russians, everybody. And, you know, we're looking at various aspects of the moon relative to like landing and all the sand issues, planning to protect various locations of experiments or living quarters. How do we operate on the moon functionally as an international effort where we can both be safe and really be productive?
Well, from my perspective, the foundational set of agreements are the 1967 Outer Space Agreement, and how we want to work and operate in space with a series of international partners is delineated in the Artemis Accords. Right now we have like 15 or so countries that have signed it. There are several that are absent. China hasn't signed it, for example. This is an agreement as to how we'd like to proceed in an open and transparent way, in full participation between the groups, developing interoperability, sharing resources, and being able to aid the others in the event that there are problems with national astronauts in other areas or in our areas working together. So I think NASA has started exactly what I think you want to do by creating that framework. So if you haven't read the Artemis Accords,
yeah,
I would suggest you study them, and if you want more information about them, let me know and I can help you with that.
Yes, so we're discussing the Artemis Accords, and we're also
Okay.
discussing kind of expansion from that as we dig deep into actually functioning and working together, which is a very interesting premise. But if you take that and put on Mars and think about how are we going to work on Mars together, protecting each other, being productive and anything, do you have any thoughts on that? Quite different than the moon.
I'm not so sure they're so different in the sense that even though we don't have the moon accords, over this next decade, as we really live out multiple missions, NASA's got on the books like 10 human exploration missions to the moon. I mean, we've been thinking about and working with and beginning to discuss with our partners. And there's an enormous amount of activity going on. So I think we'll learn how well those accords work over time, and that will also give us a framework to modify from to use on Mars.
Yeah, I just want to thank you. Process. Wonderful presentation. This is really great hearing you speak about so many aspects of this. We're looking to really get into space now. And now we're talking about details. It's very different than sending a few astronauts to the moon. So thank you so much.
Right. Bahik, go ahead.
Absolutely. Thank you so much for an incredibly inspiring, fascinating, and passionate presentation. I have to say, it reminded me of the famous physicist Richard Feynman.
Wow.
Yes, it did. I have to say. We know, and you've discussed and mentioned about dust being an issue on the moon and Mars, especially on optical instruments, spacesuits, solar panels, and so on. Is electrodynamic dust mitigation going to be used as a shield? And second and last, any biomimicry inspired solutions, surface coatings, and so on?
Wow, good question. Indeed, this concept of using electric fields to brush dust off is being studied. There's actually a couple papers out on that. But I'm not up on all the research efforts that are going on in that particular area, but those sound like some really good ideas.
Thank you so much.
Sure.
Josh, go ahead.
Jim, thank you so much for taking the time today to speak with us. It's really inspiring. I wanted to ask about your thoughts on space debris, particularly with the concerns we had with the International Space Station and the Russian satellite destruction. Are you concerned about like a potential Kessler syndrome or being locked in to Earth?
Well, relative to the Kessler syndrome, the concept of impacts occurring and then an orbit being destroyed, that's already happened. We actually have a couple places that you don't want to go anywhere near because the amount of debris that's there. The way we have to approach this is a concerted effort in ensuring that each of the missions that we launch has an end of life scenario, that we don't end up having additional space debris. The concept of creating debris should be a well-known hazard generating capability. In other words, we ought to by now know that if we're generating debris through impacts intentionally, we're doing it for other reasons. What those reasons are, I can only speculate. But we ought to avoid that. Or indeed, we do destroy a space advantage. Now, space advantage is for everyone. It's misguided to think that we can do without space. The survival of the human species relies on it. We have 7 billion people on this planet. In 30 more years, we're going to have 10 or 11 billion people on this planet. Satellites enable us to look down, determine how much land is under cultivation, to determine if each country is going to import or export. The amount of weather information that produces hazards, and therefore the ability to move people away from those regions, is critical to preserving life. GPS is critical to maximize all our resources. Even farmers use it to cut, and plant their fields perfectly, because they can get more yield than if they're just driving around, eyeballing it like we used to do. Understanding where we are in the solar system and the fact that we're not really in a really good orbit. The dinosaurs didn't have a space program. All right. And we now recognize by looking at what crosses our orbit that there's about 60,000 objects we need to start watching out for, or they're going to impact the Earth. And it's not a matter of if, it's only a matter of when. And some of these are easy city killers. Others are state killers. There's about 950 of them that are planet killers that'll kill 85, 90% of the species on this planet. They're so huge and they cross our orbit. And where are they? Okay. The concept of being able to leverage our knowledge of space is critical for the survival of this human species. And if we actively start destroying that advantage, we are dooming us to failure as a species that will live past what normal species do on this Earth, which is about 10 million years. Can we even make it to our 3rd million year? Okay, we are the first species that has the ability to leave this planet and explore the solar system. And now look what we've learned when we've done that. It's amazing. We have to leverage that knowledge and keep going. We are the first species that knows we can become extinct. Why would we let that happen? Why don't we use that knowledge to continue to grow and live and work as a unified human species as we also explore the solar system and learn to work on other planets? We have so much to gain and everything to lose. So we need to make sure others feel the same way. Others with the abilities to go into space recognize its importance, and join us in the continued peaceful uses of space. And destroying satellites to demonstrate something is not what I would call a step in the right direction.
Yeah, very good points. And I think many in the aerospace and scientific communities completely agree. But as we see with this recent incident, it's altogether possible that other nation states or even possibly private operators choose not to sign or ratify the Artemis Accords. And these things continue to happen. So mitigation becomes something of crucial importance. Yep. And I've read some very simple abstracts around various mitigation methods like drag nets or lasers. Which of these do you think are most viable, and how do you see that unfolding in the near future?
Good question. There are, as you point out, several techniques that are being investigated in terms of throwing a net around it. One of the things that NASA studied for a while was this asteroid capture capability. Well, I was excited in that particular area because that same technology could be used to capture defunct spacecraft and move them out of the way. So the more we do that area, the more we're going to learn how to do it. Now, that's very expensive to do. It may become necessary, and there indeed are a number of companies that are coming along. One in Japan that actually I think has a recent contract to be able to go and remove some debris. It's also important to note that there are space law restrictions in the sense that one nation is not going to be able to go and remove a satellite that was produced by another nation, and even if it was dead, without their approval. When we launch something, we own it, whether it's alive or dead, whether it's working or not, and it's up to us to be able to manage that. For NASA, over the last several decades now, we require everything that gets launched to have a rigorous end of mission plan so that we know it reserves enough fuel or capability to deorbit and come in if it's if it's in Earth orbit. Or, I signed the paperwork that destroyed Cassini. I didn't want Cassini flying around dead in the Saturn system when it could crash into Titan or into Enceladus. Same basic concept is we need to be good stewards of what we do in space. And that is essential part of it, is end of mission plans. Our space agencies all need to start doing that. We need to put emphasis on that in our negotiations and agreements, that we become good stewards of that resource, because it's of enormous benefit to the human race and to each and every one of the nations that participate to do so. It's in everybody's best interest. So why aren't we doing it?
Completely agree. Thank you so much. I have one small fun follow-up. If you were to place let's call it like a maximum longest date until we have human presence on Mars, what would you put that date at?
I'm planning to be alive when we step foot on Mars. Okay.
Great to hear. Thanks so much.
You bet.
Dr. Green, people are very enthusiastic. Do you have a few more minutes?
Sure.
Oh, thank you. Tasha, go ahead.
Hi, so those who are going to prepare for the journey to Mars are going to need to train a whole lot to really grasp what a mission to Mars will be like. So maybe they'll spend some time training on the moon or in low Earth orbit to also help their body adapt and to acclimatize to all those stressors. But while you're acclimatizing, you're also building up stressors that occur from prolonged microgravity and radiation in the moon. So how do we kind of determine the trade-off that like training astronauts, how much training of astronauts do you think is going to be in space for the astronauts that are going to go to Mars?
Really good question. One of the things that we're doing right now is we're developing a Mars habitat on Earth at Johnson Space Center. And we're going to stick some people in it. And they're going to live in this habitat like they would on Mars for a long period of time and learn to live and work in that environment. Some of the obstacles we recognize are not all just physical. It's really critical, and I think NASA's doing a really good job of it, that we pick the right people that can do that, that can handle the kind of stresses and the social interactions so necessary for a team to remain a team and work as a team and accomplish great things. Now, we got to do some different things. Let me give you one example. Right now, we can go to space station pretty darn easy, and we supply it with all kinds of stuff. Every astronaut's got favorite foods, okay? And so we send up favorite foods, okay? Now, sometimes when those missions are delayed and astronaut favorite foods don't show up, you know, they have to eat something else, or they eat energy bars or do a few things. And it's been noticed that they lose weight and they gain stress, okay? Because they're not eating what they'd like to eat. Those astronauts will not make it to Mars. I can guarantee it. All right. Now, if you like leftovers, if it's not critical that you have your favorite foods, and you can psychologically move through that by acquiring the nutrition you need and recognizing that you don't need to stress over it, that would be a better candidate going to Mars, because that's going to be a difficult trip, and we can't supply your favorite foods for the year or more. All right, that's a completely different philosophy than what we're doing right now, but we're going to have to make that change. That's a new element that needs to be brought in, and so not only the psychological parts, which will be, as I mentioned, even more important than ever before, but then the physical part too. This is why we started the process of working on space station for a year at a time. And there's some other ideas of where we're probably going to do that again, maybe a couple times, before we even consider going to Mars by the end of the decade. Okay.
Next is, oh,
sure.
Sorry.
I hope you like leftovers. I do. I think I can make it. You know, I'm not driven by food so much. I do enjoy food, but it's not like I got to have my favorite things every day.
Next is Paul, Mr. Park. Mr. Park, are you here? If not, James. James, go ahead.
Okay, thank you. And thank you, Dr. Green. I enjoyed your presentation. There's so much you covered in there. And there's so much that I'd like to follow up on, but I think what I'd rather ask is just generally, are there things that are available, literature in the public domain that you could recommend that would be a good, immersion in these topics, like Mars mission planning, Moon Mars in situ resource utilization, possible life on Mars, the nature of the regolith on the moon, and then we're just talking about space debris. There's so much, but it all has kind of a common theme. Can you help with that?
Yeah, in a way. There are several books on ISRU, but that field is moving so rapidly, they're sort of outdated. You could go on the Springer website and do that. Springer's got some. Springer also has some early Mars exploration missions. They're called they're the standard mission architectures or scenarios, and we've gone through like 5 of them, but none of them are going to be the ones we're going to use, because that also is evolving. So a couple books by Don Rapp, R-A-P-P, who tries to stay up on that and get a number of things out. If you want to really understand the importance of the moon, probably the best book in that area and the connecting science to human exploration would be the book by Paul Spudis that came out just before he unfortunately passed away. So that's a really good book. So there are several for you.
Thank you for that. I appreciate it.
Design reference missions, DRMs. Yeah, so RAP writes about Mars DRMs, design reference missions. I'm trying to think of the acronym. Has to be an acronym, right?
Right.
So, so he's got volume 2 out. Got a lot of really great stuff in it. Some of it, though, is already out of date, because we're finding new things, doing things in new and different ways. But it gives you a background and knowledge about some previous thoughts.
Sounds good.
Next, Stanley, Mr. Borowski. Looks like he's not here. Darren, go ahead. Darren? Well, if not, Randall. Let's see. Randall? Well, okay, Tommaso, go ahead.
Yeah, thank you so much, Dr. Green. Wonderful presentation, and my thanks to the AIAA Las Vegas for putting this together. They're the best group. So my question is in regards to new startup companies, which I'm doing one, and working on commercial space efforts. What would you recommend as websites to go to for bids for NASA projects?
Well, I would really haunt what NASA is supporting through what's called SBIRs, Small Business Research, Innovative Research.
I got the acronym.
Yeah, SBIRs. SBIRs come out from each center, and there are many that proposals can be put in, selected. You can get funded for a number of years, and then go to SBIRs 2, based on results and what's come out of that. That's a really good way. Other things are to partner with other companies that have success in these areas. There's probably a fair amount of knowledge out about past SBIRs and past winners that you then can relate. Okay, I can partner with certain groups and come in with a stronger proposal, and try that approach. And NASA's been increasing its funding in that area over the last several years, and I think that's going to continue. So I'd give that a try.
Yeah, much appreciated. Thank you so much.
Sure.
Next, RDPAC. Mr. RDPAC, you can go ahead. You can unmute your mic. Well, if not, Randall, are you back? All right. Yeah, so there are a couple more questions, but they have left. So maybe maybe I can compile those and send it to Dr. Green and see if it can answer more afterward.
All right, very good.
Yeah. All right. So this is really amazing, and I truly
Well, thank you.
appreciate Dr. Green's great speech and time for the Q&A. Very exciting.
Great.
Well, definitely invite Dr. Green back to the LA, Las Vegas area in person.
That'd be
after
good.
After the pandemic.
Yeah.
Yeah.
So what Ken and I talked about before I came on the air is I lived in Las Vegas. You know, as a young adolescent, my dad had a job transfer and moved there. My brother went to UNLV and taught math there. He just recently retired. When I graduated from Las Vegas High School, I had the opportunity to go to the University of Iowa, which I did. And I was born and raised in Iowa, you know, prior to going to Las Vegas. So I've lived in two places, you know, prior to that, Burlington, Iowa, and Las Vegas. So if you guys want me, I'm there. All right.
Definitely.
So Ken, thank you so much for the invite.
Yeah, you are a great leader and part of our family.
Well, thank you very much. That was very
we truly
kind of you to say.
support you. All right.
All right. Thank
you
again.
so much.
Bye now.
Bye-bye. Bye-bye.